So now we get into the algorithm of building a leftist heap. Now, honestly, this is a lot of text. I'm going to show you pictures of how this is set up. I'm going to paraphrase through some of this, but the pictures will really help. Let's put it that way. This is also a misnomer, as in when we're building our leftist heap, at first I show you how to do it basically one node at a time, but this algorithm actually is exactly the same if we were merging actually two big heaps together, because again, remember, we have pointers to both the roots of the trees and they would merge in correctly, well, again, using the same exact algorithm. So bear with me that right now I'm showing you one node at a time, but in reality we could do this with massive trees. Now what's going to happen is the value of the node very much matters. Again, we're using a minimum heap, so that minimum value or a node needs to be at the very, very top of the tree when everything is said and done. But the weird part is that the current node of where it's going to be placed, we check with the NPLs, but we also add the new node to the right side of the tree. And then if our NPLs, which is right here in our highlighted green here, if it's not NPL compliant, we'll actually do a shift or a swap of the children to make sure it is compliant. So if you don't get all that yet, reread this real quick first, but then I'll go over some examples here in a moment, so bear with me. So there's four basic moves that we have in our building of a leftist heap. Swing left, insert new root, and swing, insert in between, and swap children. So when we do a swing to the left here, pretend we have a very, very simple tree where we have 50 and then we've added 75. Now remember, this is a min heap, so 50 has to still be at the top no matter what. But here's the weird part. We do our swing left. If there physically isn't any kids to the left-hand side, we'll add, again, there's the original placement phase, and then our swing phase if we can do it. Now, if there happened to be another number in there, let's say there was a 65 here, we can't do the swing, and that's fine. We're doing the swing to make sure that it's actually NPL compliant, because if I was done with this, let's see, going to the left here, that would be 0, but if I went to the right, that'd be 1. That would not be NPL compliant. So that's why I instantly, if I can, go ahead and swing it to the left-hand side. So there's your leftist heap. So that's your swing left. The next one is inserting a new root and swinging to the left. So pretend here we have our original tree. We're doing our 25, and notice, by the way, 25 is less than 50, so 25 needs to be towards the top. So we link it, but in reality, 50 and 75 would actually be physically here, and then we go ahead and swing that to the left-hand side because there is nothing to the left of 25. So that's why you see that swing here and to the left, because again, originally it was actually here, and then we swing it to the left again to make sure it's NPL compliant, because otherwise 25 would be out of NPL compliant. We couldn't merge two massive heaps together. This one tricks a lot of people, so heads up, please. This is going to show up in your exam. So in this overall setup of tree, notice we've added a 55 in there. We're about to add a new node, 40. Well, here's the thing. A lot of people instantly put 40 down here underneath of 55. Well, that doesn't make sense. Remember, with the min heap, 40 needs to be above 55. It needs to be below 25. So what physically happens, and that's why it's called the insert in between, 40 gets inserted, and 55, again, really it's here, but then it gets swung to the left-hand side. So notice how every time at the end things get swung to the left, if there is space, But that's where you have the in-between, because 40, think of this as a heap. There's your min, my next min from that. I have to maintain the order from min to max in my heap. So we do have the in-between portion as well. All right, so the last one. We've done some insertion, we've swung to the left, and well, we have a problem. So in this example, the actual problem that happens of all things is actually at the very top or the root. So follow along with me. It says to get to a null, it only took me one node. Starting at 25, 50, well, I'll be darned. There it is right there in that null section right there. At 2, it takes me, or sorry, at 25, for the right-hand side, it took me 2. Went through 40, 55, and then null, 40, 65, and then null, or something around there. That's right. So how do we fix that? Here's the funny part. It's actually a really easy fix, but a lot of people also oops this up too, so be careful. So notice what I do is I swap the links for the node that is affected. Now notice that means not just the kids, the immediate kids of that node, but the kids, and everybody else in the generation all the way down. So notice this is a set of triangle here. Now it's over this side, and our little ones to the left hand side. So literally the children and all of their descendants have swapped. Position wise, everything's still the same. It's 40, 55, 65. Here it's 40, 55, 65. Positionality is exactly the same. It's just the kids have literally swapped places, and again, kids and descendants on the way down. Now why do that? Well, number one, it's super easy to code. You know how to swap links. Number two, let's do the NPL compliance after we know we had an issue. So here, we would go from the left-hand side and then see how far down before we hit a null. When we go through 40, either 55 and then null, or 40, 65. So that's at least going to be 2 on that left-hand side of 25. Now let's go to the right-hand side. Well, 50 and then, well, we get to a null there. So it's then 2 and 1, and well, frankly, that means it's NPL compliant, and we can move on from there. So in the notes, you're going to see a full built example of a leftist heap. Now, I'm not going to go over it in this video because, well, actually, I do it in that video, so go figure. But I still show you step by step. What I wanted to end on is I got the question, well, why are we always doing the left push and stuff like that? In reality, it's because of kids. Here's what I mean. So in the example that we have right here, we have our tree is not completely done, because you know when it's like this, you're most likely going to push over the 26. But why? Why are we doing that? At this snapshot, do an NPL compliance, and you know 23 is going to be out of compliance because on the left it gives you 0, on the right it's 1. That's bad news. So in reality, just like I've shown you before, we're going to swap the kids. It's going to look like 26 just gets pushed over, but in reality, there's a null in that leftmost side, and the kids get swapped. It may not look like it, but in reality, there is consistency of pushing that left. All it is actually doing a swap with a null. So I wanted to make sure you understand that. And also in this last example here, is that the node itself that is in question, as I'll call it, here we added a 52, everything's fine with that. We're going to start connecting it back up to our major root. And then we notice that we have an issue with the root. But remember, whenever we have the issue with the actual node, it's not the node itself that we fix, it's the kids. So again, we're going to do that swap in order to make it NPL compliant. So we're going to identify the number 4 is the issue and go ahead and swap its kids. Not it, but its kids. And then again, you'll see the final result at the very end. So again, it may look like it's been pushed to the left, but in reality, it's actually being swapped. The kids are being swapped. Very consistent in the entire algorithm.